So Matt Levinowitz will be talking about another case, this one involving sexual assault.
Hopefully everybody can hear me. My name is Matt Levinowitz. I'm an assistant district attorney with the Allegheny County District Attorney's Office. And the case I'm going to talk about was the case, the defendant's name is Allegheny County. And what this case involved was September of 2010, a person broke into a row house in South Oakland through a front window, opened the front window, went up to the second floor of a house, and sexually assaulted a young woman there. She was actually a student at Pitt. And the sexual assault occurred over the course of maybe an hour, 2 hours. The victim didn't keep exact time, but it was pretty lengthy, where the defendant anally, vaginally, and orally raped the victim multiple times. And the case was, I guess, difficult from a DNA perspective because the defendant wore a condom during the rape. So we weren't able to get any useful DNA from semen, which you might expect to get in a rape. What happened at one point during the rape is, at one point, the defendant spit on the victim's anus before he anally raped her. And after he left, he fled the house, the victim put her underpants back on and had them on for some period of time. And the underpants was the only item we were able to get DNA from because the victim was so upset about what happened and she took a shower after the sexual assault. And I'm not convinced we would have gotten much from a rape kit anyway had she not taken a shower. So the cutting was taken from the underpants. Certain areas were tested and found the presumptive presence of amylase, which is the presumptive presence of saliva that the crime lab does. And on the main cutting, they really weren't able to get a DNA comparison. And on what they call the control cutting, they were able to, and again, it was a mixture of DNA. The main contributor, not surprisingly, was the victim, and that's typical of what you'll find in a sexual assault case. That the victim is the main contributor because when you're doing the swabs or the rape kit, you're going to get primarily epithelial cells or skin cells from the victim. That's going to dominate over any sperm or saliva or whatnot from the defendant. The crime lab did testing, and because it was a mixture and because it was a relatively small amount of DNA material, their match statistic was 18 million to 1. And Dr. Perlin was able to test it using his method. His match statistic was 1.35 quadrillion to 1. We had some additional evidence in the case. The defendant's fingerprints were found on the front window of the house that he broke into. So we had some other physical evidence in addition to the DNA. There was some evidence that the defendant had been to this house a couple nights before and was able to target the house. He knew that there were actually 3 females that lived inside. As I stated in trial, he knew he wasn't going to run into a Pitt football player when he broke into the house. But in essence, that's what the case was about. The defendant was convicted of 8 sexual assault counts. I believe 3 counts of rape, and I believe 5 counts of IDSI for the various separate acts of oral and anal sex that he forced the victim to perform. And again, he forced her. He threatened her. He told her that he has hydrochloric acid. He would throw it in her face. And various threats that he made over the course of a couple of hours. He was convicted and sentenced to 32 to 80 years in prison. That's what the case was about.
Thanks, Matt. So I should also mention, before I start with this, that There were several cases that were lined up. Janet Necessary had the first case with Ralph Skundrich, which only went to trial about a month ago. And Rob was working on one, but Matt's case was the first one that actually went to trial. It was the first use of TrueAllele in the county. And if you look at the date of March 2012, that was about a month or two after the appellate court ruling. So that was very good timing for Matt, who didn't have to do a FRI hearing. What I'd like to walk through now, briefly, before I come to the last section about DNA databases and societal safety, is to, again, walk through this case. Now that you've seen this sort of presentation and you're more familiar with the concepts and it's becoming more evident, I'd like to walk through again what the jury sees, and maybe this will be even clearer than it was 15 minutes ago. So we begin with Commonwealth versus Akan, computer interpretation of quantitative DNA evidence in March of 2012. You're all experts on this now. You know what a genotype is. A genotype is the genetic content that a person has expressed in allele pairs at some location or set of locations in their genome, and it's distributed in trillions of copies, which is why when people spit or bleed or leave some sort of biological material, it can be in abundant enough amounts to be detected experimentally. Okay, so a genotype is a pair of alleles at a locus that represents just one possibility out of maybe 100 possible allele pairs at that locus. This was a mixture. What the lab did and what we did conceptually was the same. They did DNA evidence interpretation. The data was generated by the lab by amplifying it. First it's extracted, then it's amplified, then it's separated out by size with different fluorescent dyes, and that produces these signals. When the evidence data is looked at by a person or by a computer objectively, then a person might say, well, the alleles 10, 11, 12 are in there, or not say anything at all, and give some information, whereas a computer approach can make better use of the same data and pull out certain possibilities and give them varying probabilities based on the data that it sees. After a genotype's been inferred, and only afterwards, can a comparison be made with a known genotype to objectively compute a match statistic. Okay, in this case, these were the data peaks at one of the 15 genetic loci. This was a D3, and there are two low peaks at 15, 16, two higher peaks at 17 and 18. And so the x-axis is showing which allele it is based on how large the molecule is. The larger molecules move more to the right. And the relative fluorescence units, or RFU, show the relative amounts of more of these two alleles than the presence of the smaller two alleles on the left. When people analyze the data, they draw a line through the data, either by machine or on paper, however they do it. And this threshold cuts off the data, removes the pattern, and reduces it to a yes or no question, which produces what might be alleles or might not be. There's an error rate in any procedure. And these peaks are then labeled as allele events. And out of the 4 possibilities, there would be 10 pairings of these alleles. If you have 4 objects, there are 10 ways of pairing them. The first with the first, the first with the second, the first with the third, and so on. Okay? So, something that a computer can do, and it's indicated here in gray, it's not necessary in a case like this, is it can assume that an individual is present in the mixture. For example, a victim. If the victim's at a crime scene and there's a sample, the computer can analyze the data, either assuming there are 2 unknown contributors or assuming the victim is present, and then searching for one unknown contributor. Like anything in science, if you can nail down more of your knowns and reduce the scope of unknowns, you can get more information on occasion from the data. Okay, and so here's a victim allele pair. This would be another possibility, and this would explain the data, but the computer's not just trying this, it will move these rectangles all over the place, try out 10, 15 as an allele pair, 11, 18 as an allele pair. Those don't explain the data very well, so they end up with lower probability. And in fact, most of the probability, 99% of it, is concentrated at that 15, 16 on the left of the two smaller peaks. Okay? It gives a little bit of probability to other events. They're not impossible, they're just much less probable. And this is the genotype of the individual who is not the victim at this genetic locus. And we still don't know who to compare it with, but we're about to, because now we need a match statistic. We have to compare this evidence genotype that's concentrated almost all the probability at one location at 15, 16 against the 100 possible allele pairings, which are shown in brown. But I'm only showing the ones that appear on this picture, not the ones that would stretch for 100 feet. And then we can look at this and say, well, the chance that somebody actually has a 15, 16 is 18%. It's pretty common in the population. The chance that have a 15, 17 is maybe 15%. And these numbers would add up to 100% for the whole population. Now we're told to make a comparison with the genetic type of the defendant, Mr. Khan. And that's a 15, 16. And so we focus, of all the different comparisons we could make, or that are made by the computer, we focus just on the 15, 16 to form the match statistic relative to Mr. Khan. And we ask how much more does his genotype match the evidence genotype relative to a random person. And that ratio is around 5 of the blue bar to the brown bar, that 99% to the 18%. That becomes the match statistic. Doing this for all 15 loci, and here again is the scale of going up to 100 as the match strength for 15 different genetic locations. The numbers are multiplied together, and then we can answer the question, is the suspect in the evidence, by saying that a match between the evidence and the suspect is a quadrillion times more probable than a coincidence.